everybody. So welcome to the morning session. So our first speaker today is Peter Cholak, who is going to talk about Ramsey-like theorems on the rationals and the Rado graph. So thank you, Vivek. Thank you, Dennis and Andy and anybody else involved in the organization of this conference. It's great to see so many young people and so many people, like students of mine, showing up to talk. You know, I guess you had enough, and you're still coming back.
Yeah, no, it's great stuff. I'm looking forward to it.
All right. Anyway, so this is going to be a kind of a survey talk on basically countable structures that have finite big Ramsey degree. I'm going to explain what that is in a minute, and I'm going to try to highlight connections with computability as I go along. And parts of this talk are very suggestive of future work. I'm just trying to frame out some maybe future research directions and questions as I go along. And the viewpoint's mine, and the errors are mine. And I've also been a little bit neglectful. I didn't include all the references. There is a large paper that I wrote with Paul Elliott, Emir, who didn't wake up yet, and Benoit and Ludovic. Thank you guys. It's on the archive, and I'll reference it occasionally. But also this talk draws heavily on discussions I've had with Natasha Brennan in the back and Andy Zucker over the period of time. Okay, so let's get going here. So by the way, I like questions and comments during the talk, so please ask them. Okay. And I've given this several times, so every time I find an error, so hopefully well, probably it's not error-free yet, but we'll see. We good? Yeah. Okay, so all right, so let's talk about what structures we're going to talk about here. So the natural numbers. So, and by the way, there's a language. I'm thinking about with the language, right? We're logicians here, so when I think about the natural numbers, I have no language that I'm considering. Okay, there's no language. The rationals they're ordered, so there's a language. There's the left end. And then also various different graphs, right? So there's basically the nodes and there's edges, and there's several different types of graph. I have here the Rado graph, the triangle-free Henson graph, the K3 Henson graph, and basically the graph that avoids any finite graph G. Okay, so we'll talk about these objects as we move forward. So all these objects are homogeneous, universal, countable structures in a finite relational language. Could be an empty language. Okay, so I'm suggesting what we have here would work for a homogeneous, universal, countable structure in a finite relational language. Okay, so let's define what I mean by some of these terms. So homogeneous means that for every finite substructures A and B, so B and B hat of A, if there's an isomorphism between them inside the structure, then I can extend that to automorphism of the whole structure. And most of the time it's going to be an effective automorphism. And you can go back, and I'm not going to check that these structures actually satisfy these properties. So this is that's homogeneous. So let's do universal. So universal, what we have to have is we'll start with the collection K of finite finite. They're all finite structures in some finite relational language. And so some examples, and these examples line up to the examples I gave earlier. Okay, so all finite sets, so it's no language. All linearly ordered sets, right? So one language, and then all finite graphs, all triangle-free graphs, all K3. Okay, you got the idea. Okay, so those are my possible finite collection of things. And so basically, a structure A is always going to be countable. Okay, A is universal for this class K if every finite substructure of A is in K. So every if you take the rationals, any finite substructure is linear order. Okay, so it shows up. Okay. Every subset of the naturals is a finite set. Okay. And now for all finite substructures C of A, all right, so you take some finite substructure C of A, and all B in K extending that C somehow, okay? Not necessarily, whoever the domain is, okay? There's basically a substructure B hat of A with an isomorphism between B and B hat. In other words, any possible extension you could get in K, you could get in A. Okay? And so that's what I mean by universal. Okay, and so for all these structures I talked about are homogeneous and universal for the corresponding collection K. Okay, and so I didn't put down. I mean, hence would be a good reference for this, but there are other references, and it's computable. Okay, so again, I'm not really saying that. Okay, so that's what we need. All right, so now, okay, so I wanted to actually, here's great drawing. I got this out of the Louvre. It was
Yeah, the primitive art. One of these cave drawings.
Okay. So anyway, so I wanted to at least outline what the possible B's are for various different structures. Okay, just so we know, right? So for the naturals, right, it's just points, so just vertices. Okay. I mean, maybe, you know, I guess I could have used a different program instead of my hand to pull this off. But all right, then for the rationals, right, they're linear orders. I put the black thing to go through that. And then the red is supposed to be the edge, right? So for the Rado graph, and this should be labeled, this is the Henson-Fried, you know, triangle-free graph. Oh, and I see I blew it because this avoids, so this one's wrong, right? Because this is supposed to be triangle-free, and there's a triangle, right? So you just have to erase this edge, and you know, it's supposed to be this one going on. Anyway. Okay, but I just want to point out that those are what the structures look like, and you can do this for all kinds of different things. Okay, so for size 4 and so on and so forth, right? So okay, so we got a handle on these objects. All right, so let's talk about what it means to have big big Ramsey degree. So I'm looking at A over B. Is all the isomorphic copies of B in A. Okay, and so I have this notation: A arrows. What does that? What does this mean? That means that if I have a coloring, if I had a coloring of all the copies of B in A, K coloring of those things. So all the copies in B are colored, right? With one, possibly K colors. There's an isomorphic substructure A prime of A. So what I'm looking for is not a homogeneous set. I'm looking for an infinite structure that looks like A. Okay, and that's where this A comes from. That I wanted that this object should be homogeneous in some sense, right? And should be looking like A. Okay, and here what I want is the number of colors. So if I just restrict my copies of B from being within A prime, they have less than L colors. Okay, and L, I'm going to call L type if there's actually a coloring where I have to use all L colors. Okay, I can't get away with fewer than L colors. Okay, and so just to put this in framework that we've talked about, Ramsey's theorem says basically for all n, right? So I'm thinking about Bn is just a finite structure of Bn. For all K, so all K colors. So for all K coloring of the naturals, there is a copy of the naturals, so a homogeneous set, where basically I just use one color. Okay, so all right, so now we have to be a little bit careful because Ramsey's theorem is very suggestive here, right? And we certainly do this, that a tight bound should always be 1, okay? But that's not going to be the case, yes?
So I think you do have a typo.
Possibly.
The F inverse should be just F.
Yes, yes. What is the F inverse doing there? There should be no F in. Yes. Yes, just none. So what I said was correct. I want to make sure that I have. Yeah, you have to. What I said was correct. Yes. Okay. So I have at least one error in this talk, possibly more. Right. Only if I don't do anything. But yes, I want to just make sure I use the number of colors I use is valid. Okay. Okay, any other errors or comments on this slide before I move on? All right, okay. So, okay. Questions? All right, so this is a slide that tells you what a finite big Ramsey degree is. So a finite structure B in A has finite big Ramsey degree if there's basically for every coloring of copies of B in A, I can find an isomorphic copy of A where I use just L colors. Okay, And we say that basically B has big Ramsey degree L if the bound L is tight. Okay? And a structure A has finite big Ramsey degree if for every finite substructure B has finite big Ramsey degree. Okay? And so a theorem is that all the structures I'm talking about have finite big Ramsey degree. And moreover, for all the finite substructures B of A, there's a tight bound. Okay? And so I included, I didn't include all the references. I included Ramsey from years ago, and Natasha, because, yeah. Anyway, there's another connection I was hoping that I could, some other joke I could say, but I'll have to wait on that one. Anyway, so great. All right, so any comments? All right, so I want to explain what it means to say big versus small, right? Why are we saying big, right? So let's talk about
Can
that.
I read the theorem again? Sorry, I got distracted with the joke.
Oh, I didn't say the joke.
But I got what it is.
It says that all these structures have.
All those.
What's that?
The ones in your example.
The ones are my examples, right? And I guess I'm suggesting really, and I think, I don't know, Natasha could, basically if you're a universal homogeneous language and a relational language, you should have finite big Ramsey degree. So, yeah.
With some qualifiers. We know it for pre-nomination classes and binary languages.
Yeah, so that's some talk. But, okay. I mean, it's suggestive. But all the structures that I have certainly talked about. And so, okay, so what happens, Antonio, here, if you want to pin me down, I will like reduce the number of structures I'm talking about. Okay? So, I mean, certainly with the naturals, I got it, right? Okay, so that's how it's going to work, right? When if you want me to get concrete, I will do so by eliminating these structures. Yes.
So is the B not a problem usually because it's things are homogeneous, like it's just easy to.
The finite B?
Yeah, because with the natural numbers.
Well, I don't want, okay, what I don't want is like, I don't want, okay, so I want relational languages. I don't want a functional thing, so, because like if you take the closure of B with a function, you might get an infinite structure. I want to avoid that. But any finite structure I take is fine. Does that make sense?
Yeah, I guess I was just wondering, is it trivial in the proofs of for the other structures to, because what do you need with B? You need it to be
It's just like pick a domain, a size of the domain, and then just pick about all the possible ways you could have that. All right, so those are some of the possible B's for some things. Well, not
yeah, so your homogeneous set has to have the characteristic that all the B's have the same color.
Yep. Yeah, so for example, if I looked at the Rado graph, right, and I wanted to look at basically all colorings of the three-clique, right? So then I would have to ask that basically, I don't know how many colors I need, let's say 2, I think it's 6 actually, but how many colors I need, I want to make sure that I get a copy of the Rado graph where I use just 6 colors. Even if I do it.
I get it, yeah, so it's not really any harder for when we go away from the natural numbers.
No. Yeah, so that, I'll just repeat that example. So I take a coloring of the Rado graph where I basically use 10 colors on this triangle, okay? And then I want to get a copy of the Rado graph where I use 6 colors. Right, I think that's the correct numbers. Right? I mean, so if you want to pin me down on the actual numbers, I'm going to go back to the naturals too. Okay? So, all right.
So, but how important from your slide, a couple of slides on, the number depends on B, right?
Yes.
So how?
Well, we're going to find out in a little bit. I am going to tell you something about that, okay?
That's right.
But not everything. All right, so let me go and explain what a small versus big is, okay? So K has small, so this is now the collection K, a small Ramsey degree. It basically, for every A and B in K, there's some larger C, okay, such that basically, if I color in C all the copies of B, I could find in there a copy of A, where all the copies, in that A, all the copies of B use at most L colors. Okay, and so finite Ramsey theorem is a great example because basically if I pick some n and r, right, I could find some large set, right? So if I color all the n tuples or the n sets of M, right, I could get a homogeneous set of size R. Okay, and okay, so all of these corresponding classes have small Ramsey degree. Okay, and of course, if we, we would love to understand these tight bounds, right? And even for just Ramsey's theorem, it's still unknown, right? We had a discussion, was it? Someone remember the joke? Erdős said if you had to find out, if you want to Ramsey for 5, right? They said you had a year to get the Ramsey number for 5. Okay, you could do it, but at 6, right? Well, the cause is lost. And so there is a connection that has to be worked out more concretely. I'm not going to go to that between big and small Ramsey degrees. Okay. And so, and I should point out that I can't pronounce these Czech logicians, combinatorics or logicians. They really had a big impact in actually, on these small Ramsey degrees, right? So that's a big industry in Ramsey's theory of understanding these structures. What you could say about them.
How is K, little k quantified or
What's that?
up there?
Up here? This one?
Yeah.
It's got to be bigger than L.
So there is a C and an L and a K.
Okay, so K, for all K.
If K is little k is the size of.
Let's replace L, K with L plus 1.
Okay.
All right, so I just,
You can remove one column.
I got to remove one color, yeah.
So the theorems together is that they all have small and big Ramsey.
That's right. That's right. But they're different proofs. With the Ramsey theorem, you have this connection via compactness, right? So that is more tenuous here, right? Because you have these structures B that you have to put together, right? In some kind of nice way, and that doesn't always work through compactness, right? I mean, you could get a large sets and put them together. They're going to be a mega, but not all the C's you might put together give you the corresponding A. Okay. Other questions? Okay. All right, so 2 typos or so at least. All right, so now let's just try to figure out. So here's an example where the number of colors has to be 2. Okay. Okay, so now I'm making some choices. So I've got the rationals here. And I'm going to consider them. Okay, so we get the rationals. We get to decide how we get to code them. Okay, we get to decide all kinds about things. So I'm going to code them here as the dyadics. Okay, this is my choice. Okay, you could argue about the choice later. We'll do that in a second. All right. So I've actually concreted them. So we have basically Q sigma is a particular rational between -1 and 1. Right. So there's an ordering. Right. It agrees with the lexicographic ordering on the tree. Okay. And now I'm going to color these things. I'm going to color them basically 2 pairs of 2 rationals. Going to be color 1 if the corresponding representation of the one is smaller than the representation of the other, and they're linearly ordered, and the 0 otherwise. Okay. And now I claim that any subcopy of Q in this, any copy of the rationals inside this copy of the rationals must have pairs that are ordered 0 and 1. Because you just take a point. All right, my tree grows up because trees go toward the light. Okay, so you have a copy of a point here. You're going to have something over here that's going to be bigger than it in the rational ordering that has a higher thing, and the same thing goes over here. They have to have both sides. Okay. All right, so we have to have 2 copies. Okay, and so really the key thing goes on here that I'm looking at the copies I'm looking at are countable. Okay, so. I mean, we could play a game when it's not countable, but that's someone else's talk. I went to the circus on Saturday, and the performer was heckled from the audience, and the performer said, "When it's your turn up here, you could do the tricks." So, anyway, So the issue is that Q is countable. And the same argument works however we enumerate K, right? So you can think about the rationals. So however you do that, whatever ordering, whatever your favorite copy of the rationals is, you have some enumeration. Fix that enumeration. In that enumeration, you have, if you have a subcopy, you have some copy, right? You have to have things. There's only finite many things that you enumerated before it, right? It's a well order. So you have to have things that are, you know, above it in your enumeration that are less than it, and above it that are less than it. You have both those colors. So, okay, what happens is that we could, in some sense, add this relation to our structure, okay? And in some sense, we do. So if we add this relation, right, that tells us how they relate in terms of this enumeration, then basically the number of colors we had in this example show up from the types, right? So model theory, you guys know any model theory, right? You should. So, right? I gave this talk last week, and they're like, I don't remember my model theory, but counting types is important, right? So, okay. All right, and so, okay. And also, I just want to point out that really, this is going to be important later, is that I can make the gap between the representation from one rational to the other very large, arbitrarily large, right? In other words, when I say something is large, I mean, you give me a number, and I just have to get something bigger than that number, okay? That's what I mean by large, okay? So you pick your rational, and then, you know, you give me another number, I have to be higher. If there's going to be something bigger than that over here that's less than it, on the other side too, okay? So I can always make them arbitrarily large. All right, okay. Any questions on this? Does that help somewhat? All right, what we'll do, I mean, it doesn't help completely. Okay, so this example suggests that the number of realized types of B, right, so, okay, so what I mean is really the types, right, in model theoretic sense. In some language, in some extended language provides a lower bound of the big Ramsey degree of B and A, okay? So in other words, you know, I was able to add this, you know, this relation, R I added was the kind of definable from my structure, and I could just put it on there, right? It's there, right? So I have to count those things, right? So certainly those types provides a lower bound of these things here, right? And you know, so in the right extended language, I'm not going to explain what that is, okay, necessarily, right? And I don't think we completely understand the right extended language for everything that we're talking about. For the right extended languages, the number of types gives you a lower bound, okay? But it doesn't tell you anything about an upper bound. Okay. So, right, just because I know I need two colors, right, for the rationals, right, doesn't mean I can get away with two colors, right? I have to prove something still. Okay, so we're gonna really wave our hands at this. So okay, so we're gonna work towards trying to understand why we just get away with two colors. So all of our structures are countable. Okay, so I'm gonna kind of now fix a representation uniformly of all these structures. Okay, and I'm going to use basically some nice collection or subset of 2 to the less than omega. Okay, because that's countable, right? And what am I going to do? I'm going to include some nice. I'm not going to actually write out the details of what I want. I'm just going to avoid the complex issues. Okay, but what I'm going to do is I want these things to be nice. Okay, we all want to be nice. Okay, so but what do I want? I want it to be an anti-chain. Okay, the strings, I could do that. And let's say I only want one string most one string of each length. I may not have strings of every length, but I want one string of every length. And somehow I want some ordering or relation on these things that basically I could basically take this copy of the structure and say, oh, I can map it. It looks exactly like 2 less than omega. Okay, so I could just, it looks exactly like 2 less than omega. Okay, and then maybe I'll have to label some of the nodes and stuff like that. Maybe, okay, we'll avoid that for now. Okay, all right. So here's a sketch of a sketch of a sketch of, get the idea of that basically, that B has big family of Ramsey degree in A. So we have a coloring, okay, we have a color, okay, so inside, we fix our enumeration A, right? And we've colored all the copies B in that enumeration in A, okay? Now what that does is that induces a coloring, so what we have to be careful is that each copy of B has to correspond to some subtree of some fixed height in my copy of 2 less than omega. So I have to be careful that when I have this copy of B, it has to be coded nicely by some subtree of height, whatever height I want, like 3, 5, whatever it is, right? And so in there. So that what I'm claiming is that when I colored A, I actually induced the coloring of basically subtrees of certain height inside of 2 less than omega by my nice color. Does that make any sense? So I basically, the picture is hard to think about, but I colored A, which is a copy of 2 less than omega, right? This is isomorphic to 2 less than omega, right? So when I look at the copies of B, when I reflect those back into this copies of 2 less than omega, I get basically these trees of subheight 2 less than omega. And I don't want to go through the details because it's complicated. And now what happens is there's a great theorem, and I'm not going through the details. It's just I'm waving my hands at this, right? It's like the boat passing down the river, very fast, right? I'm going to use Milliken's theorem. Milliken says that basically if I've colored trees of certain heights, right, I could basically get a copy of 2 less than omega where all those trees have the same color, right? So I'm going to use a copy of Milliken's theorem, okay? And now what I have to do, and that gives me, that allows me to eliminate, and I have to do this then one for each type to get a nice copy of my things. So basically when I take this copy of B and I pull it back, right, there might be multiple ways to code it up depending on how that structure shows up. So I might get different, there's no one canonical coloring for these subtrees of height, just in omega. Okay, a sketch of 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 a sketch. Okay, so that's it. So the idea is basically I've colored my copy of 2 less than omega. I've used Milliken's theorem to pull this back and I push it back and I push it forward. Okay. Now at the same, so that gives you the number of colors. Now at the same time, so this is really, so at the same time, one has to completely understand the realized types of B and every isomorphic substructure A prime of A. Okay, and then hopefully they coincide, right? What you've worked out coincides. Okay, and I consider these proofs as tour de force, right? They're very complicated, so lots of things play together, and one slide doesn't do justification, but that's not our goal. Yes.
Yeah, can you say more about what you mean by all of the realized types coincide, or?
Well, so the thing is, I need to do this some number of times. And hopefully the number of times that I do this corresponds to the number of ones I discovered here. Okay. So, and the issue, why do I have to do that, is each one of these may give me a unique tree. Well, or give me a color on that tree, right? So, right, there's different ways to distinguish these types. I don't want to go through the combinatorics. But, right. Okay, that's a proof. I mean, all right, okay, so here's the computability theoretic question. So we have a coloring, K coloring of all the copies of B and A, and our goal is to find an isomorphic substructure A prime of A. And again, there's my typo, shows up multiple times, where the number of colors is actually L. Okay, and I want to know, where does this, it's not a homogeneous set, but where does this A prime live in the arithmetical hierarchy? Okay, is it in the arithmetical hierarchy, and if so, where? Okay, right, I mean, so this is a standard question for Ramsey's theorem, right? If you have a homogeneous set, where in the arithmetical hierarchy is it? Is it computable, is it not computable, so on and so on and so forth. Okay, all right. Okay, so there was an error in my first slide here. So if I just look at, I want to dismiss singletons, okay, and this is certainly, I'm going to what I say here is true for the first three structures I consider, which are the nationals, rationals, and Rado. Basically, I can do the greedy algorithm. I don't want to deal with this, right? In other words, by the way, I'm thinking about my structures is computable, my coloring is computable. I'm claiming if I just color the nodes, I could get a copy of the rationals or Rado, or the rationals where I use one color, okay? And basically, it's just the greedy algorithm. You try what you could do, right? You extend to get more and more and more, and if you fail, then you can reduce, right? You reduce the number of colors and repeat this, right? So it's non-uniform, but you could actually do it. And there's so here's the first problem, is do the same for the Henson graph. And so there's other people working on this. It is known to be arithmetical, but tight bounds are not known, okay? And the issue is, when you reduce, what happens, okay? How do you get the copy that you deal with, right? So you're just doing the obvious thing in terms of how to build from K these copies, and then you fail with one color. How do you use what you've got left to get what you continue? Okay. All right. Okay. So Milliken's tree theorem. So the needed instances of Milliken's tree theorem that we used here, or that were used here, are arithmetically true. That's what we proved. Okay. Now I wrote this carefully. I hopefully wrote this carefully. The needed instances that we use it through. So, but not computably true. Okay. So what? I mean, there are some instances of Milliken which are computably true, but we didn't need them. Okay. So I tossed in a little reverse math. I'm not going to say it because I didn't know what it was after that conversation yesterday. So I just want to put out, so Milliken theorem for height n, and so just give you a relationship, it implies Ramsey's theorem for height n. Okay, so stronger, right? And for n equals 2 is actually strictly stronger. Okay, so it's a stronger statement, right? It might be the kind of the natural strongest kind of common kernel property like that, right? It implies everything we need that we've talked about. Okay, so I didn't say this very well earlier, but on some of these sketches of the sketches here, right? I said we used Milliken's, or a recent extension of Milliken's, right, to get this, right? So I didn't say what that might be. Like, say if you label the nodes, you have to actually reprove Milliken's with the labeled nodes, and then you have to do something different. Okay, so those extensions we don't know anything about at this point. Okay, so does what I said above hold for those needed extensions of Milliken's theorem? Okay, and also really what are the exact arithmetical bounds about these various different, that's still also unknown. I mean, that's been very well studied for Ramsey, but not here. Okay. All right. Now, I guess, so I should say something here. Let's say that it's not, for some instance, it's not arithmetical. I don't know if it's true or not. I mean, right now the proofs seem to be non-arithmetical. If it's not arithmetical, right, for some finite instance we need, right, that would mean that some finite Ramsey degree, and maybe that would reflect that corresponding small, or the corresponding, B, you couldn't prove that in arithmetic, right? So that would be kind of interesting, right? If you, in other words, if you had an instance of this finite big Ramsey degree, which is not provable in arithmetic. So I don't know if I believe that. I think they're all provable, but we'll see. Okay, so here I want to say something about this. I just want to say, reverse math, something or math. So now, what do we have? We have that. I just wanted to repeat what we have here. We have that all the structures have this finite big Ramsey degree. And now, what I want to claim, and this is something that people have to prove along the tightness, and tightness kind of basically appears computably. So what I want to claim is that there's some computable copy of A, all right? And then for any B I want to think about, there's a computable coloring of those copies of B and A, all right? Such that in every copy A prime of A, there are basically many copies of, this is the second typo, of many copies of B with color J appearing. In other words, that basically I have this computable coloring, right? In any copy A prime I get, right, there are infinitely many copies of B with that color, okay? And I have to use all those colors, right? So this kind of witnesses that, this coloring witnesses the number of types I need. Right, so this is, I'm just made it a coloring because it's easier to think about this way than thinking about the types.
What is L A prime?
This should be B here.
But more to the left, L sub A prime? Or L sub
Should also
A?
be a big
Comma, yes, L sub A comma.
J less than or equal to.
Yeah, this should be B too. Is that what you want?
Okay.
Yes, I mean, I'm copying B, yes. All right. Okay, and so I want to say, so basically what I'm saying here is that the number, the L sub B appears computably, right? I can pick it out computably whether this happens or not, right? And it was suggested from the types earlier before anyway, right? That what I suggested that would happen, right? So this is there. But I also want to add a little bit more to this conjecture as I go on. Okay, so I want to code the halting set into the, this is Carl's proof that Jockish, that we basically can code the halting set into the Ramsey theorem for triples. And I just want to repeat it because it's important to remember how it goes. What's the coloring going to be? I have basically a triple X, S, and T. Basically, it's 1 if basically K, and there's typos in here. Not, well, somewhere. Oh, look, there's typos in here. So basically, if K restricted to X is the same, in other words, K hasn't changed from, K up to X has not changed from stage S to stage P. Okay. And now what happens is, let's just go through the proof. I take a homogeneous set, okay, and the number of colors I did again is what is this inverse in there? Well, anyway, the number of colors, I think the point is that that's right. No, whatever, okay. Anyway, so the number of colors is 1. So now what happens, I want to go through the proof. How do I compute K? I pick a Z. Okay, I want to know what happens to K on Z. I pick a large X in Z, right? So I have to have a large X in there, right? It says infinite, so it's something bigger than it. Now there's a large S bigger than X in H, so it's basically K is settled down by that. Right, now all I need is something basically bigger than S in H, right? So I got that color, that triple's colored 1. Okay, so I want to put some names to this. So basically a triple is a substructure of H, then there's a large, so there's these large X, T prime, S double prime, and T double prime, such that basically the triple, well, these triples are all substructures, right? So I can make these triples there. And I say that the triple is largely extendable in H, and I'm going to just call the new triples I got large companion of the original one, okay? So really the second large companion tells me that the color must be 1 from the argument I had above there, okay? And what happens with the other one is that the other one says that if what I have for, if they agree at Z at stage S and T, but they don't agree in the end, right? Then there has to be a larger color that does that, right? So this tells me that, so we can't basically, we're going to play this game a little. We can't have clusters. If we have multiple colors, we can't have clusters to give me the wrong answer. Okay, I need to have that going on, right? So I can't get the wrong, so I'm not just saying, later I'll have more colors, okay? And so basically this tells me that basically all the triples in here have color 1, right? And I could read off from that what happens with K. So, so now I want to take that and move that over to all my structures. So all of our structures are countable. All right, so there's an enumeration, right? So I've been using this nice subset of 2 less than omega. So I could just let, I want to give it some length or some number, right? So how about the length of the node? Okay, and so now when I would say my enumeration, I would think the I is in the main is large, if basically the I is large, okay? So now when I think about something large, I want to think about that. And so now if B has size 3 or whatever, bigger than 3, we could use this I'm not going to go through the details, this notion of large and find what I mean by copying B when it's largely extendable and has large companions. Okay? All right, and so now, okay, so now what happens is, due to the universality of what we have here, for all B, so for all B, whatever, how we define largely extendable, for all A, and for all our copies B in any substructure A, I got all my primes, any substructure A prime of B, there's typos there. So any substructure, they're largely extendable, because it's every substructure is universal, right? So if I want to have a large extension, and take any copy B I want a large extension, in the finite sets, there's a large extension that does what I want that's very, very large, and there's an isomorphic subcopy of that does that, boom, right? So that's true, right? So everything is largely extendable in my copies, right? So this is the conjecture here that probably in some of these things has to be proven, okay, for some of the structures. For all B and for all A, for any, I got the primes, any substructure A of A prime of A, and there is some I, such that there are infinitely many copies of B, such that those copies of B and infinitely many of its large companions have color I. In other words, some color I, for some color I, all right, I have copies of B, where B and all of its companions have color I with respect to this particular coloring, okay? I think it's true for all I, but I nailed it down for one I, okay? It doesn't matter, right? And also, moreover, in A prime, we can actually find infinitely many of these copies, right? So we can computably find these copies, okay? And so, by the way, once you know you have something that has large companions of color I, so in other words, I tell you B has large companions, you can just look for it, right? Because you know it always has large companions of color I, you just start looking for it because everything's computable, okay? So once you know this, so all you have to do is really prove that basically any copy of B, you just have to do what happens here, you have to do with respect to the coloring B, right? This happens because of universality. Now you have to actually do this in this structure here, right? And it should happen. Okay. All right, and then once you got that, well then you could use Jockish's coloring, right? This could use the product coloring. Okay. Okay, so you can use the product coloring, and I'm not going to go through this, but so that tells you that. So what does this tell you here? Is that when you're looking at substructures of psi 3s or more, so I'll do reverse math. It's equivalent to ACA naught. It's arithmetic comprehension, right? So these structures are these theorems, when B has size 3 or more, give you basically all of arithmetic, and they're proven on arithmetic. Okay, this is, again, if you pin me down exactly what I will say, I'm going to reduce the number of structures, right? And the question is, as we move on, is that always going to be the case? Okay, so for 1. It looks computable. For 2, you get everything, your arithmetic. Okay? So what happens for 1, you get looks computable. For 3 or more, you get everything in arithmetic. All right, what happens to 2? All right, so there's a dichotomy to what happens with 2. What happens for the Rado graph and the rationals is different. Okay, and what happens in general is unknown. Okay, and I should have added here that the Rado graph. Well, let's just see. So R is a Rado graph. So now I'm coloring basically K2 is just a pair of edges that are connected. I'm coloring basically edges, okay? And I'm using 3 colors, right? This is for you, Paul, right? Right, so I'm using 3 colors. And I want to get 2 colors out in the end, okay? Because with the theorem, the same thing I had about basically, if you have an enumeration in the Rado graph, if you have some node, you're going to have things that are large that are connected to it. It has to have 2 copies. And so now this does code avoidance. So basically, pick some C that's not computable. There's a copy R prime at B where all the copies of K, the edges, have just 2 colors, and R prime doesn't compute C. Okay, so this is code avoidance done by forcing. We're not going to go through that. But anyway, so this copy of R prime well, if I choose C to be K prime, this copy of R prime doesn't compute K. So it's weaker than arithmetic. Okay. So it's very similar to what happens with Ramsey's theorem. So you know, you can study this statement, how it compares to other statements weaker than, you know, there's this reverse math zoo, right? And so how this fits in there is still really open. And you could read it in there and figure out what happens out a little bit, right? And I can't remember how it compares to Ramsey's theorem for pairs offhand, so I apologize, because that would be the natural question. I think it's stronger, but I can't remember. Anyway, okay, questions? All right, now what happens here? So this behaves like the Ramsey theorem, classical Ramsey theorem. All right, so the rationals. The rationals. So there's a coloring of pairs of rationals that every subcopy of the rationals, where the pairs are colored by exactly two colors, computes K. Okay. All right, so we don't get counterpoints. We don't have code points. So what happens? What's different? Well, what happens there is that in the extended language that we have for determining when we put everything together, the meat of two rationals is definable. Let's just see why that might be the case. Right? We have a two type, it's just two elements. It's actually a three type, right? Because what happens? The two type, you have two elements, right? They have different levels in the tree, right? And they're an anti-chain, right? So if they're an anti-chain, right, well, they have a meet. That object is definable, okay? And so, you know, their meet's assignable. So in other words, with the rationals, the meet is definable from these things. So you have to look at the meet closed things of this, okay? All right. And so then what happens is that, so this is suggestive again here, that these three types realize the largest connection in the extended language conjecture. And we could use Jacques' coloring as well. Okay, so this is suggestive. If I mean, I didn't write down the details, but other types might also include the meet or some other. There are subsets of it. There's no function going on there, but they might be able to have a meet or some other object, right? They may not just be, n tuples of size n, they could be something you get definable from them, right? They existentially closed, right, objects, right? So I think that in the larger language, the corresponding types actually realize the largest conjecture. Okay, so I'm projecting that. Okay, I think this is the last slide here. So let's go back to the Rado graph and see what happens here. So now I took a concrete example of the Rado graph, okay? So I just want to point out here that, so what I could do with the Rado graph, what I've done in this first bit here is I defined a dense linear order bank with endpoints. So basically for each node in the Rado graph, I defined sigma I, right? So basically there's an edge, sigma I is 1 if there's an edge from I and j. Okay, these are nodes. They're ordered by less than, by the normal lexicographical ordering, and it turns out to be a dense linear order without endpoints. Okay. Now what happens is you could get isomorphic subcopies of this copy of the Rado graph, where that ordering is not a dense linear order without endpoints. Okay. So in other words, you take your Rado graph, you get a subcopy of it, but under that fixed ordering, it's not no longer a dense order, right? If you redefine it for that particular ordering, the subgraph you've chosen, it's going to be dense order, but not the original one. Okay, so the point here is that really your subcopies of the Rado graph need not preserve this order, right? But with the rationals, the subcopies have to preserve the order, and so the meat is kind of tossed in addition, right? So that's what happens, right? So you have to be a little bit careful. This is a survey talk, it's a skimming of what happens.
So the sigma i's are elements of Cantor space?
Yeah, yep.
Not finite. Okay.
They're finite, yeah, so I meant them to have a height I.
We're looking at the J is larger than I.
I'm looking at, I have a typo, it should be J less than I.
Okay.
Or I should be sigma J. Yeah, so I got.
So you are coding with finite sequences?
I finite sequences.
Okay.
Yes, yes, thank you. The errors are mine. They're just to keep you on your toes. All right, so that's all I've got to say. So.
Okay, thank you very much. Are there any questions? Yes.
Yeah. Have you thought about the ordered Rado graphs? So your language is edge.
What disordering?
No, not with that ordering. So you've got two binary relations. You've got the edge relation and the less than relation that you put. No, not that one.
I mean, we have thought about an ordered Rado graph, whether it's the one that you're thinking of or not.
So is the phrase say limit of the ordered graphs, the binary ordered graphs?
I don't think so.
Because it might have, well, yeah, it would be interesting.
I don't know what that ordering looks like, to be honest.
No, it's just the rational, so what you end up with a homogeneous structure, which is a Rado graph, with a dense linear ordering on it.
Is it this one?
No. Because you have two binary relations, you have the edge and the less than.
But wouldn't then the two binary relation be coded with via Milliken's tree theorem for
No.
ternary?
Well, so that's not known. I have a result using coding trees that gets the exact data.
So the answer is probably no. If they're different, if it's different than this structure, right, if they're not bi-interpretable, then the answer is no.
Yeah, they're not bi-interpretable.
Yeah, so then we did not look at that structure. Yeah, like I said, there were a number of places there's problems. There was a number of typos and there's problems. There's the ones I identify were a problem, but there's also lots of, I mean,
Real problems.
there's, you know, yeah. Yeah, I wrote, yeah. So at some point, I wrote a paper that people call CGS. I wrote that and there's lots of questions. And so then everybody answered the questions. So this time people have to figure out their own questions.
Okay, any other question? Oh, so no question on the chat as well.
Move on there.
No. Okay. So if there are no other questions, let's thank the speaker again.